from my last lecture, I started discussion on an important subroutine which we often use in power system planning, okay, and also in power system operation. Okay. And this is called load flow or power flow analysis. And since as I said, the distribution networks are mostly operated in as radial network. So, we need a special type of load flow or power flow analysis approach, okay, and that is one of the approaches I will talk about here, and that is very simple approach. That is basically the applications of Kirchhoff's current law and Kirchhoff's voltage law in a iterative way, okay. And this is called forward backward sweep load flow or power flow analysis. Okay. So, in order to discuss this approach, I took an example of a simple 6 bus or 6 node distribution network, okay, 6 node distribution network. And in my last lecture, I discussed how to prepare these two important data files which are required for this power flow analysis or load flow analysis approach, and this is how we use this node data and this line data information in order to perform this forward backward sweep load flow. Okay. These are essential. So, one should know how to compute this data file first. So, I started my discussion with this, and then there are many things like how to convert these quantities to per unit. This I discussed, and how before that how to choose the base voltage and base volt ampere or base MVA, those things I discuss. And then in this part I discuss two important steps. One is called backward step, another is called forward step, or one is called backward sweep, another is called forward sweep. Okay. How to perform these two steps, this I discuss considering this example. Once you understand these steps, you can even to write the program codes on this particular iterative approach in order to solve this power flow of any type of distribution network. Of course, the condition is to be satisfied that the distribution network need to be radial. Okay. So, that is the important consideration here. So, this approach will work for radial network only. Okay. And in this particular slide, I discuss how to calculate. In fact, I chalked out how to compute this line current from the load current information in backward sweep, and then also I discuss how to calculate or how to compute the bus voltage of all the buses using this forward sweep. Okay. And these two steps we need to iteratively use while getting the final solution. Now, if you look at this backward step, here firstly we determine this load current, we firstly determine this load current from this available information that we have, because most of the nodes in distribution networks, they are of load nodes. So, we know that what is the power demand. Power demand means active power demand and reactive power demand of that particular node, okay. Or rather to be more precise, this is the load demand of all the loads who are connected to that particular node. So, this is aggregated load demand of all the loads or all the customers who are connected to a particular node. So, this P 2 is basically representing the active power demand of node 2. That means that it is basically active power demand of the aggregated loads who are connected to the node 2. So, there are any number of customers may get connected to a particular node, okay. And this P 2 or P 3 or P 4, this power demand or active power demand specify the aggregated demand of all the loads who are connected to these nodes, that is node 2, node 3, node 4 respectively. Okay. So, this one has to understand, and as I said, the computation of the line current is the main challenge of writing this generalized program code on this forward backward sweep load flow algorithm. And one can do either by tracing out this, that how many nodes are beyond a particular node, like this is one approach. Okay. So, once you trace down that this node number 3, 4, 5, 6, they are the nodes who are beyond this node 2, because this is very important, because if you look at this system from this particular node, this power is flowing through this node number 3, 4, then 6 and also 5. Okay. So, if you know that what are the nodes beyond this any particular node, for example, beyond these 2 we have node 5, node 3, node 6 and node 4, then one can find out what is the power actually flowing through this particular node, that is node 2. And once you chalk out that, okay, you can easily compute the line current which is flowing through this node number through the line which is connected to node number 1 to node number 2. So, this is one way, and another way already I discussed. This is how you can find out this line current from this node current. You need to first find out the terminal node, and that is why let us start the end entry of this NR here representing this receiving end nodes. Okay. And of course, this 3 6 means the 6 is the terminal node, beyond that we do not have any load nodes. So, you start with that, and then you find whether this 6 is appearing any time to this NS data. So, obviously, it is not appearing, and then you can understand that of course, there is nothing beyond this node 6. Okay, there is nothing, and the node 6 is one of the terminal node. So, you start with this line current computation using this available value of P 6 and Q 6. Once you get that, this will be the line load current. Load current means the current drawn by all the loads who are connected to node 6. Okay. So, once you get that information you store in an array or in some temporary memory. Now, next you go to next node, that is node 5. Again you check whether node 5 is appearing to the sending end node or not. So, it is not appearing. So, then you can understand that node 5 is also a terminal node. That means, beyond that we do not have anything, node 5 is also a terminal node. So, if it is so, then of course, we can calculate this load current, and that load current would be the line current which is connecting this node 5 from node 2. Similarly, this from node 6, that load current would be equal to line current which is connecting node 3 to node 6. So, now you proceed to the next node, you will get node 4, again it is also not appearing in the sending end side. So, it is also a terminal node, and you follow the same principle. Then you come to this node 3, and here you can see node 3 is all appearing in the sending end data 2 times. That means, node 3 is not a terminal node. So, it is connected to node 4 as well as node 6. Now, here you can do one thing, that you first determine the load current at node 3. Okay. In fact, load current is independent to all these nodes. So, you can compute it means prior to this particular operation, and then while determining the current flowing through this node 2 to node 3, you have to also consider this load current of node 4, because this node number 4, its demand is coming through this line which is connecting node 2 to node 3. So, whatever current this I 2 3, it is function of this load current at node 4 as well. So, it is function of load current of node 4. Okay. So, that is why we need that. Okay. Otherwise, if you look at this line current which is connecting this node 3 to node 4, since it is node 4 is a terminal node. So, it is independent of the load current of any other except this node 4. So, I 3 4 which is the line current which is flowing from this node 3 to node 4, it is independent of load current of any other node except this node 4. So, it is only equal to the load current of node 4. So, this is something important one has to understand, that is why I am focusing or I am emphasizing this in very detailed manner. Okay. So, same thing is applicable for other terminal nodes like node 5 and node 6. Okay. So, in node 6 this line current which is flowing from node 3 to node 6, it is independent of any load current except the load current of node 6. So, that is why I 36 is equal to this load current of this node 6, that is I L 6. So, I 36 is equal to I L 6. If you apply KCL at this node, you will get this current incoming current is equal to the outgoing current, that is I L 6 and so. So, for terminal nodes, there this line which is connecting to the terminal node. So, the line whose receiving end side is the terminal node, it is only equal to the load current of that receiving end node. Okay. And that is one needs to understand, and that happens for all these terminal node 6, node 5 and node 4. So, any line which is connecting this terminal node, its line current equal to the load current of the terminal node. Okay. But this is not applicable for any intermediate node, that is at node 3 this line current, that is I 23, it is not only depend upon the load current at this node 3, but it also depends upon the load current of node 6 and node 4 as well. And that is why you can trace down this who are there beyond this node 3, and that is done in one of the approach, that beyond this node 3 we have node 4 and node 6. So, the line which is connecting this node 3, whose receiving end side is terminated at the node 3 or whose receiving end node is node 3. So, its line current is equal to its own load current as well as the load current of node 4 and node 6. So, here one thing is assumption that there is no losses. So, losses are not considered here because in a particular power, I mean, so when this power flows there are some amount of losses which I will come later on. Okay. Now, when you get that, so node 3 its line current which is connecting this node 3 at the receiving end side, its line current would be equal to load current of this node 6, node 4 as well as node 3. So, how to find out this? So, one way, as I already said, by tracing down the nodes who are beyond a particular node prior to this approach starts. Another way is that you can first see that at node 3 how many times it is appearing in the sending end. So, here it is appearing in 2 times, one is this, another is this. Okay. So, you take the corresponding receiving end side load demand, that is load demand at node 4 and load demand at node 6. Then again you have to see that whether load 4 and load 6 appearing any times in the sending end side. If it is appearing, then again the corresponding receiving end load should be added. So, that you can compute the line current for the line which is connecting node 2 to node 3. These things happens when you go to node 2. For example, you see node 2, you have to check first that whether it is appearing in the sending end side or not. Yes, it is appearing twice, one is this, another is this. So, corresponding load current, that is node 3 load current and node 5 load current is to be added. Then you have to again check whether this node 3 and node 5 they are appearing in the sending end side or not. So, node 5 is not appearing. So, you can assume that it is a terminal node, but node 3 is appearing. Okay. So, again you have to perform the operation for node 3, whether who is connected to node 4, node 3 at the receiving end. So, I got node 4. So, I will add this load current of node 4 with this line current, which is connecting 1 and 2. Okay. Now, again you have to check whether this 4 is appearing in the sending end side or not. So, it is not appearing. So, I can terminate the process. Otherwise, I have to again perform this operation till I finished it to the terminal node. So, this is something like that. At this node 2, you first see that who is connected to this 2. So, 3 and 5 are connected. Then again 5 is terminal node. So, beyond that there is nothing, but 3 is not terminal node. So, again you have to see that who is connected to 3, who is the receiving end side for the line which is connected to this 3 node 3. So, I got this node 6 and node 4. Okay. So, I have to add this their corresponding load current. Now, if somebody some other nodes are beyond this 4 and 6, you have to means continue the process till you reach to the terminal node, and that is why we first compute this terminal load current, because they are independent, and then we process this to slowly to the substation side. Okay, because this line current which is connecting this node 2 to node 3, that is I 1 2, it is function of all the load currents, okay, because it is near to the substation, it is connecting to the substation. But this line current which is connecting node 3 to node 4, it is independent of load current for all other nodes except this node 4. So, I could calculate it even though I do not know the load current of any other nodes, and that is why I start this process from the terminal node. Okay. And since the process is started to the terminal node, and then we move ahead, or we move in backward, we started at the end node, and then we perform the whole operation in backward direction, and that is why it is called backward sweep. Okay. Whereas, this in forward sweep, which is basically used to determine the bus voltage, we start from the substation bus, because at the substation bus my voltage is specified. So, I know that what is the voltage at the substation bus, okay, and no other nodes this voltage is specified. Okay. So, since the substation voltage is specified, we start this we can start the computation of the voltage which is connecting the substation to the other node. So, here connecting node of the substation is node 2. So, I can find out what is the voltage at this node 2 just by subtracting this line drop which is connecting node 1 to node 3 from this node voltage or substation voltage that is specified. Okay. So, once you get that, so that will be the updated voltage at node 2. Okay. Then we go to this next line which is connecting this node 2 to node 3. I know the updated voltage of node 2. So, I can calculate this node 3 voltage simply by subtracting this line drop which is connecting node 2 to node 3. This line drop is I 2 3 multiplied by Z 2 3, okay. And I 2 3 already computed, because line currents are already computed. So, you can compute this voltage. Without computation of line current, you cannot compute the voltage drop, and that is why this line current calculation or line current computation should be done first. So, that is why a backward sweep is to be done, and then we can compute the voltage. Okay. So, then we move again to the other node which is node 6 or node 4, and we can calculate their corresponding voltage by simply subtracting the line drops, and that is how we move. And since we start this operation from the substation bus or substation node, and then we move to the other nodes. So, its operation is in forward direction, its calculation or computation is in forward direction, and that is why it is called forward sweep. Okay. So, I hope this is understood. If it is understood, then we will discuss that how long we will do this iterative operation, because as I said these two steps, that is backward sweep and forward sweep, this we need to iteratively do for several iteration. Okay. So, before we stop. Okay. Now, the question is how long we will do this iterative operation. Okay. So, we will operate the this iterative operation till we satisfy some condition, and that condition is called termination condition or termination criteria. Now, there might be a unique termination criteria or there might be more than one termination criteria. Okay. So, of course, one termination criteria is to set maximum number of iteration, maximum number of iterations which need to be executed, okay, which need to be executed. So, this is one termination criteria, but this is not all, means we will not keep this operation if we get convergence in between. What do you mean by convergence? Convergence means here if we basically here our goal, as I said, is to determine this bus voltages, okay, in a iterative way. Okay. Initially, we take a guess value, that is a flat voltage guess value. We consider initially that all node voltages are equal to 1 per unit. Okay. And after performing this forward step, I get these voltages are updated. So, voltages will no longer be 1 per unit. Okay. So, voltage will deviate from 1 per unit, and if this deviation from this guess value or to the next iteration voltage is within a given tolerance, then we can consider that okay, we have achieved the convergence criteria and we can terminate the program or we can terminate the iterative process. Okay. And that is why the second termination criteria is error in node voltage from previous iteration to current iteration. Okay. So, this maximum number of iteration, let us consider is max iter, and we can set a particular value, let us say 50 or 100 or 1000, whatever it is. Now, if you use a sole termination criteria for this maximum number of iteration, that we will terminate after that many iteration, then what will happen, that if we get convergence much before, then we unnecessarily need to continue. Okay. So, I will come to that, and that is why second termination criteria is very important, that if we achieve the convergence. So, this is basically measure of convergence, measure of convergence. This is a measure of convergence. If you achieve convergence much before this we get this maximum iteration, we can terminate the program. Okay. And that is why this is a measure of convergence. Suppose if we set max iteration or maximum number of iteration is 100 and we achieve the convergence after third iteration or fourth iterations, then unnecessarily we need not to continue till this 100th iteration. okay, we can terminate after getting this convergence. But it may so happen that you will never get convergence, then you have to terminate after some point, and that is why this maximum iteration is set. Suppose even after this maximum iteration we do not achieve convergence, then also I have to terminate it. I have to terminate the program, I have to terminate this iterative process, so that we can conclude that we may not get convergence, the load flow is not converged. Okay. Now, how to find out this error, this voltage error? So, these voltages, these bus voltages, they will constitute a bus voltage matrix, okay, or bus voltage vector. For example, V, if we represent V iter, it means that it is a matrix which consists of the bus voltages which we get at iteration number iter, that iter may be 1, 2, 3 and all. So, here we get these bus voltages V 2 iter, then V 3 iter. So, here you can take this absolute value of these voltages, because this voltage whatever you are getting this voltage are phasor. So, I will take them their magnitude only. So, this V is basically the magnitude of all node voltages at iteration iter. So, this represents all these node voltages at iteration iter. So, this correspond to this end of this this buses, I can say it V n iter. Okay. So, this is basically the matrix or the array which consists of all the bus voltages which we get after executing this iteration equal to iter. Okay. That iter, if it is 2, that means it is the bus voltage matrix, or it is the node voltage matrix which we get after execution of iteration 2. Okay. Similarly, for any iteration you compute that, and then you in order to find out this error at any particular iteration, let us say iter is equal to iter plus 1, it is basically equal to this V iter plus 1 minus V iter. Okay. And then whatever you will get, you will take the absolute value and you will take the max of that, you will take the max of that. So, max, this is basically error is basically representing the maximum mismatch, of node voltages from previous iteration to current iteration, previous iteration to current iteration. Okay. So, it gives maximum mismatch, okay, or it gives this maximum value, maximum absolute value of maximum absolute difference of all the bus voltages among all these bus voltages which we get from one iteration to other iteration. Okay. So, this is the main convergence criteria. If this criteria is satisfied, we can terminate the iterative process. Now, even if after execution of maximum number of iteration, if we see that convergence criteria is not achieved, then we have to also terminate, and that termination will lead to the fact that this load flow is not converged. Okay. So, there may be some conditions that this load flow may not converge. Okay. Okay. So, this for this condition we will keep this second termination criteria. Now, we will try to make the whole thing in a common form, and so that one can understand how he or she will write this program codes for this for executing this forward backward sweep load flow algorithm, and this can be represented, the whole process can be represented in a flow chart form or by writing pseudocodes. So, here I will write pseudocodes for that. Okay. So, in order to write pseudocodes, we will begin this program. Then the first thing that you have to specify is your specify this ITR max, that is how many number of maximum iteration you will execute. And here you can see there is one thing I missed here, that this is how we can compute this error. Okay. And this convergence criteria is that if this error of one particular iteration, let us say iter plus 1, okay, if it goes below a given value of tolerance or given value of accuracy, this tolerance or accuracy, then we can consider that we can terminate the program, and that is basically this criteria. So, this error in the node voltage from previous iteration to current iteration needs to go below a specified accuracy value. This accuracy value you can set as 0.001 or 0.301 or 0.201, that is up to you, which gives that if this maximum error from of this node voltages from current iteration and previous iteration goes below this value 0.001, that means maximum changes, maximum mismatch of this voltage value goes equal to or below this value accuracy, then we will terminate the program. Okay. We will terminate this program. Okay. So, and that is why this is the main convergence measure. Now, first to specify this ITR max, that is how many maximum iteration up to which we will do this computation, and we will also specify this accuracy, that what value of accuracy or tolerance you are desirous to get. Okay. What are the desirable value of accuracy or tolerance. So, first to specify that, and then the second thing we have to specify base values, that is base voltage and base volt ampere. This volt ampere can be in kVA or MVA as per your choice. Then you need to call to data files, call data files. So, what are the data we require to compute this load flow analysis? We have two important data files, one is called node data or bus data, another is called line data. So, we will call this node data and bus data. Okay. So, after these data files are called the data files. So, after these data files are called, you have to do this per unit conversion. So, next step is per unit conversion. So, we have several parameters which need to be converted to per unit. Since we know this their values as well as we know their base values, we can convert the per unit. So, what are the quantities normally we need to convert to per unit? We need to convert per unit active and reactive power demand, active and reactive power demand, and line resistance and in reactance, right, resistances and reactances. So, okay. So, this we can do prior to our iterative operation starts, and this will be this will remain same throughout this iterative process, because active and reactive power demand will obviously not change, and line parameters or line resistance and reactance will not change. Now, how to convert this active and how to convert this per unit means one quantity to per unit quantity, this is mentioned over here. So, this is the process by which we can convert. This is per unit conversion process. This already I discussed in my last lecture. First, you convert this active power demand and reactive power demand to their corresponding per unit values. Voltage is already in per unit. Okay, voltage is already in per unit, and then you compute this resistance and reactance of the line into per unit, okay, by dividing to the corresponding base values. Okay. Now, after doing so, we will start this iterative process. So, we specify the first iteration as ITR equal to 1. So, that is basically first iteration. Okay. And in order to start this iterative process, we have to call a loop. Okay. And you can there are several ways to call the loop, either it can be a for loop or it can be a do while loop or whatever. So, here basically we will call do while loop. So, what we will do? We will check two convergence or two termination criteria. One is convergence criteria, another is this maximum iteration criteria. So, while this ITR less than equal to this ITR max, that means, this is the first first termination criteria, whether iteration, it is a check whether this iteration current iteration number is less than equal to the maximum iteration number that you have set, whether this is, and there is another convergence criteria that you have seen, that error. Okay. So, this error initially when you start this first iteration, error is equal to, you have to specify a value. Okay. So, error you specify a higher value, and then before you execute this program, there is no error actually. So, you have to specify error value, a high value, and then you specify this error goes then below certain accuracy value. This is the second termination criteria, which is called convergence criteria. Okay. And if both the conditions are satisfied, then you perform this next procedure. So, what is the next procedure? First procedure is backward sweep. Next procedure is forward sweep. So, if this condition satisfy, you do this operation. So, this backward sweep is for determination of line current, to determine the line current, and forward sweep is to determine the bus voltages. So, if we write it here again, this is to determine line current, and this is to determine node voltage. So, after performing line currents and node voltages, after performing these two steps, you will get the updated voltage, you will get the updated voltage. So, whatever updated voltage we will get, let us store this updated voltage within this array. So, now we have this V. Now, after doing so, we will make a iterative count, that is ITR is equal to ITR plus 1. And then next what we will do, we will compute this VITR, or here in fact, you can do one thing, instead of this error specified to this ITR to ITR plus 1 to ITR, we can also specify it like this ITR minus 1, okay, because we have already added this iteration count by 1. So, when if you have done so, after execution this operation, then our ITR count will be, iteration count will be 2. Okay. So, then you find out this error, determine error. Okay. So, after doing so, you get this error value, and you this is also something which will iteratively updated, which will be iteratively updated. So, now for example, that when first operation of this loop, so when iter will be 1, you perform this backward sweep and forward sweep. After that, you make this increment of this iterative count by adding 1. So, we will achieve this ITR equal to 2. So, this error will be giving you the error from iteration 2 to iteration 1. In iteration 1, this bus voltages are all these initial gauge values, which are we considered at 1 per unit for all the buses, and for this current iteration, that is eta is equal to 2, this now voltages will be updated voltages of all these buses or all these nodes. Okay. So, once you get this determination of error, we will we will make this end while, and again this will go back to this loop. It will check these two condition, whether this error goes below this accuracy or this ITR less than equal to ITR max. So, this time ITR will be equal to 2. So, 2 will be lesser than ITR max, because normally we set it to some value, say 100 or 50. Now, when we go to iteration 2, so the first condition will be automatically satisfied, and if the second condition is also satisfied, so it will terminate this loop. Okay. After this termination, you check whether ITR is equal to ITR max. If it happens, then we will call this load flow didn't converge. That means we did not get the convergence. Okay. Otherwise, you print the result, particularly these voltages, node voltages and angles. Okay. So, this will give you uh, actual value of these node voltages and actual value of node angles. So, this is how this pseudocode works. So, this whole process is called pseudocodes. The whole process is pseudocodes. Codes for forward, backward, sweep, load flow algorithm. So, this is the pseudocode for forward backward sweep load flow algorithm. These pseudocodes the student can implement in whatever language they are comfortable with. You can implement it any language, whether it is MATLAB or Python or C, C++, whatever language you are comfortable with. And these codes should be written in such a way that these codes will work for any distribution network, and that is this need to be generalized. Okay. If we change this data file, from this any node system, from 6 node system to 30 node system to 100 node system or 2000 node system, so your program will work and it will finally give the converged value of bus voltages and angles. So, whatever I discuss in this lecture, this is basically written in slides form. So, here we took this single line diagram of a typical distribution network to illustrate that. You can see this is a 5 node system. So, this is a 5 node system. Okay. So, we have this node 1, that is substation, and all other nodes are connected to customers or loads. Okay. And this is basically illustrated, so that you can understand this whole operation, but already I took this example here, and I hope this example is understood, and similar kind of example is given in pictorial form in this particular slide. Now, there are some important information that one needs to understand, that first of all, why we convert this per unit conversion. As I said, before your execution of the program, we need to convert, we need to follow this per unit conversion of all this available information like active and reactive power demand and line in parameters. Okay. Now, why do we do this thing? Now, this is basically followed not only for this particular load flow approach or power flow approach, this is applicable for any type of load flow approach, whether it is a Newton-Raphson, whether it is a Gauss-Seidel or fast decoupled, any type of load flow or power flow approach which we follow this per unit conversion. Okay. Now, why we give this per unit conversion? Because it also gives a relative magnitude of various quantities. Per unit means we bring down the quantities in between 0 to 1. Okay. Now, when I will show you, in fact, I have some results for different distribution networks after execution of this forward backward sweep load flow. I will show you how this node voltages are usually represented. So, since we convert all these quantities into per unit, this voltage they change, voltages change within a very narrow band, okay, and we can get a comparative information. For example, if we consider this substation voltage as 1 per unit, and at node 2 I get a voltage of 0.99 per unit. So, this gives a clear idea that there is a 1% of voltage drop which take place between the line which is connecting this node 1 or substation to node 2. Okay. So, this is means these quantities they vary from a narrow band. Now, if we say that node substation voltage is 11 kV and this this node 2 voltage is 10.998 kV. So, that may not give you the comparative comparison so easy or so quickly. Okay. So, we can make relative magnitudes of various quantities. Also these values these per unit values vary within a narrow range, and it makes the computation analysis much easier, okay, and whole things will be much understandable. Second means one of the important features is that this per unit values of voltage, current and impedance are same for both primary and secondary side of transformer. So, it is independent whether which side of transformer you are considering this. Okay. So, this you can see and you will understand. Okay. Now, this is how we convert per unit quantities, how this calculation or computation to per unit quantities we do. First we specify this base voltage and base MVA, and from that we can calculate this base current and base impedance. Okay. And from this we can compute this, we can convert these line parameters into per unit, and sometimes base can be changed. So, if the base is changed, how to get this computation, this is shown over here. But normally in load flow or power flow approach, you do not change the bases, okay, for a particular network. Now, this is the first step, as I said, we have to prepare this data file, and these are the quantities we require to create this data file. Already I mentioned we need to specify these base quantities, these are the base quantities, that is base values and base kVA or base MVA. We need to also specify this minimum voltage error or accuracy value, also maximum number of iterations, which I already mentioned, and we need to also have the available information of line parameters and active and reactive part demand, also which is another important thing that which is not mentioned over here, which is missed, is information to network topology, information of network topology. Now, how we basically translate this information, this is already I mentioned while creating this line data file, that is this is basically translating this network topology, the sending end side and receiving end side data, and this is very important to calculate or to compute this line current. Okay. So, these are the information we require to create these data files, these are the informations we require to create this data file, and after getting all this information, we compute this bus data or node data file. So, this already I mentioned, it will it is almost in standardized way we will do. First column 1 will give you a node number of bus number, column 2 will give you this bus code or node code, column 3 and 4 of this file will give you this initial guess values of voltages and angles, and column 5, 6 will give you active and reactive power demand. In basically this distribution network not in megawatt MVA, rather they are specified in kilowatt and kVAR, okay, because distribution network load is not in megawatt range normally. Okay. Then we prepare this line data file as well by considering this connectivity of nodes, okay, and by providing the input of line parameters. Okay. And this is the step of computing this line current and bus voltage. So, these two steps are used for line current computation, line current computation, and they are done basically in backward sweep. Okay. And this is the step for node voltage computation. and this is done in forward sweep. Okay. So, these are basically the applications of. So, this is basically application of KCL, application of Kirchhoff's current law KCL, and this is basically application of Kirchhoff's voltage law or KVL. Kirchhoff's voltage law or KVL, and with the simple application of these two, we get without any mathematical complexity, we get the solution for all the nodes voltage. Okay. This is the flow chart. Okay. So, you can see this flow chart is similar to our pseudocode that we have written today. We read this data file, we initialize these bus voltages with flat stat. Also, we need to specify this maximum iteration and accuracy limit. Then here we perform this 2 steps. So, this and these are backward sweep, and this is basically forward sweep. Okay. So, after performing these 2 steps, there is a this while check whether this accuracy is achieved or whether we have exceed that this or whether we have reached to the maximum iteration, and accordingly this loop will be loop is created and it will be iteratively updated. Okay. Now, I have some results of different distribution networks data. Okay. So, first data that I want to present is 69 bus or 69 node radial distribution network. Okay. So, here we have one feeder. So, if you look at this network, so this is one feeder. So, this is a single feeder network, and why it is called 69 bus or 69 node distribution network, because we have 69 numbers of nodes here, nodes or buses. So, this is the main feeder, this is main feeder, okay, and this arrow they are representing, you can see all these nodes are associated with some arrow, and they are representing this load demand of individual nodes. Okay. And apart from this main feeder, we have some laterals. So, this is one lateral, this is one lateral, this is another lateral. So, these are laterals. Similarly, here also we have laterals. Okay. So, we have one this is also a lateral. So, we have 1, 2, 3, 4, 5, 6, 7 laterals along with the main feeder. So, we have single feeder network with one main feeder, with 7 laterals. Okay. And you see that this main feeder is from node number 1 to node number 27. Then from 28 we have one lateral, this lateral, then this will up to 35, and then from 36 we have another lateral. In fact, node number 3 is connected to 2 laterals, one is from node 28 to 35, another is node 36 to 46. Okay. Then node 4 is connected to one lateral, this is from node 47 to 50. Then node 8 is also connected with a lateral which consists of 2 nodes, node 51, node 52. Node 9 is connected to one lateral which is having node 53 to node 65, and similarly node 11 and 12, 2 laterals. Okay. This is what 69 node or 69 bus distribution network. So, first we have to compute this we have to create this bus data file. So, this is giving the bus data file. You can see this bus number is specified in the first column, bus code is specified in the second column. So, except this slack bus, all are 0, indicating that the all other buses are load buses. Then here column 3, column 4, these are gauge values of bus voltage and node voltages and angles respectively, and column 5 and column 6 represent this load active power demand and load reactive power demand in kilowatt and kVAR. Similarly, we have a line data file here, which is represented in this slide, and here you can see this N S representing the sending end node, and N R is representing receiving end node, and R and X are corresponding resistance and reactance. They are probably in either per unit or in ohm. If they are in per unit, that is fine. If they are on ohm, that means you have to convert them into per unit. Okay. So, this is the bus voltage magnitude plot of this 69 node system or 69 bus system. Here this all node voltages or bus voltages are plotted over this node number. So, here this voltage at this point node 1 is 1 per unit. Then you can see there is a dip in this voltage magnitude till this point. Here this is node number 28. Why there is a dip? Because up to node number 28 we have this main feeder, node number 27 we have this main feeder. Then node number 28 is basically close to the substation. So, that is why its voltage is higher than this node 27, because node 27 there is a that much of voltage drop, and this is very far away from the substation, and there are several nodes are connected in between, and there are several lines. So, if we subtract this line drops, so nodes 27 will give very less amount of voltage, whereas this node number 28 which is closer to the substation. So, its voltage is higher than 27, and that is why there is a sudden increase here. Okay. So, this is actually main feeder profile, voltage profile. Then these are the voltage profiles of one lateral. Then again this is some voltage in between, some node number in between 40 to 50. Again this there is a dip in the voltage. Let us see why it is so, because there is a from 36 to 46 we have a longer lateral. So, that is why this voltage drop takes place. So, there is again a voltage drop, and we get some nodes, that is node number 65, which is correspond to the minimum amount of voltage. Okay. Minimum amount of voltage. Again voltage is higher in other lateral. At node 66 probably one lateral starts, 66 there is another lateral starts, and that is why here this is somewhat bigger lateral. So, here at this point we get least voltage magnitude, Then another lateral starts, which gives bit higher voltage, and that is how this voltage profile can be described. Okay. Now, these are the values of these bus voltages in per unit or load voltages in per unit. So, this is the complex voltage which gives you voltages as well as this angle. So, if you take the absolute value of this will give you voltage magnitude. If you take the angle of this will give you the voltage angle. Now, this is another distribution network which is having 3 feeders. So, this is one feeder, this is one feeder, this is another feeder. So, this is suppose feeder 1, this is suppose feeder 2, this is suppose feeder 3. So, we have 3 numbers of feeders here, and this we have several laterals which has this is one lateral, this is another laterals, this is main feeder, or there is this is another longer lateral, and so. So, here we have this is main feeder, having several laterals like this. So, this gives how a practical distribution networks will look like. Okay. A distribution networks might have multiple feeders, might have each feeder may associated with one or more than one main feeders and along with several laterals, one main feeder only along with several laterals. So, similarly, for 52 bus system we have created this bus data file here in similar way and line data file here, and this is the voltage profile. Okay. This is voltage magnitude plot. So, here again you can see the dip in the voltage from starting from the substation to the some nodes value here at node number 19, because node number 19 is the least means farthest bus. You can see node number 19 is the farthest bus of one of the farthest bus of this node now from the substation. Then after 19 another feeder starts. So, again this voltages increase to the substation voltage and so on. Okay. And so on. So, this is how this 52 net bus net node system work. Okay. Then this is again this voltage in value of this 52 bus system in per unit. From here you can get the magnitude of the voltage as well as angle. And this is another radial system which is called 33 node system or 33 bus system, having one main feeder. It is also a single feeder network. It is also a single feeder network, along with some laterals. This is one lateral, this is another lateral, along with three laterals, one main feeder, and three laterals. Okay. Three laterals, and these other things are similar. So, this is how we can create this bus data file for that particular system, and also line data file is given. From these two data files one can find out this voltage magnitude plot. You can see similar voltage magnitude plot is here. So, up to 18 there is one main feeder, then 19 is lateral starts. 19 lateral starts, which is closer to the substation than this farthest point of this main feeder. So, its voltage magnitude is higher. Similarly, this voltage magnitude of 23 is higher, because it is near to the substation. So, this is how this bus voltage magnitudes plot look like. This is again this value that we get after execution of all the iteration, and this is of course in per unit. Okay. Now, we have a summary of results which gives the some important parameters which we use to assess the performance or operational performance for a network. One is called minimum bus voltage. Now, what is minimum bus voltage? That we get all this in per unit. This is in per unit. So, minimum bus voltage we get in for 69 bus system, it is 0.9092 per unit. For 52 bus system or 52 node system, it is much lower, 0.6843, that correspond to 32% voltage drop, where here we have 10% of voltage drop, which is somewhat acceptable, but here it is very high, high voltage drop. Similarly, here also it is 9% voltage drop, and also this least voltage magnitude occurs at which nodes or which buses. So, here for 69 bus system it occurs at 65th bus or 65th node. Similarly, for 52 bus system it occurs at 50th bus or 50th node. Similarly, for 33 bus it is 80th node. And maximum voltage is of course except substation, they are near to the substation, and the power loss, it is computed in kilowatt. For 69 bus system it is 225, for 52 bus system it is bit higher, because its voltage profile is very poor, and for 33 bus is 202 kilowatt, around 202 kilowatt. So, this gives a comparison, and these are the some important parameters we assess in assessing the operational performance for a network. Okay. So, these are the references from where I took many concept, This is the where you get this idea of forward backward sweep load flow algorithm, and these 3 will give you the data files. So, this will give you the data file of 33 node system. This file will give you the data file for 69 node system. One can download this paper and go through and get the data, and this reference will give you 52 node system. So, you can go through this paper in addition to what I discussed today, in order to have a more finer information. And finally, thank you very much for attending this lecture, and this will finish you module 4, which is one of the shortest module in this course. Thank you.